right, this is section 4.4. We're talking about trig functions. The only thing is we're not looking specifically on a unit circle now. We're going to start expanding out to any point in the coordinate plane and how to work with that. So as I go through, let's get a little bit more colorful than we have in the last couple of days. We're going to look at any coordinate, any angle in the second quadrant. Okay, so let's draw a pretty picture. Any angle in the second quadrant. Let's go over here. We're going to call this XY, and I'm going to use this to make a triangle, and we always make our triangle with the x-axis, okay? R is the distance from the origin to the point. So R is the distance from the origin to the point, and we know to get to that point, I go over X and I go up Y, okay? So as we look at this, basically how would I find R if it's not 1? I could use Pythagorean theorem, where R is going to be the square root of x squared plus y squared. The biggest thing though, R cannot be 0 or we don't even have anything, we'll be stuck at the origin. So that's the big thing. So let's take a look at sine. We know sine is the y value, only this case our radius isn't 1. So sine, our angle always goes over by the origin. So the sine of our angle is the opposite over hypotenuse, so y over r. Again, a stipulation, if r is 0, then we don't have a triangle. Okay, so we don't want that to happen. Cosine is the adjacent over the hypotenuse, so x over r, and again, we want to actually have a ratio. The third one, tangent, is opposite over adjacent. We want it y over x, and again, if there is no length, then we'll be right here on the x-axis or the y-axis, which we don't want to happen. Cosecant is the reciprocal. R is over y. Again, we're not going to be looking at those major points on the axes, so we want to kind of stipulate what's going on. Secant is r over x. Again, we've already stipulated x can't be 0. And the final one, cotangent x over y. And again, we don't want y to be 0. Okay? This is the same thing. You're going to draw triangles. It's a lot of 4-2 review. The only thing is we're going to actually have to do more work than just a radius of 1. So kind of keep these in mind. I try not to remember these. I just draw a picture and let my picture help me kind of go through it. So let's scroll down. Let's try a couple. Okay? Suppose that I have this point, -5, -12. Well, that is in the third quadrant. So let's draw a picture. -5, -12. Let's go here. We're going to make a triangle with that point and the x-axis. My angle is always near the origin. And if I labeled these sides, I had to go left 5 and down 12 to get to my point. Now, what's the only side we're missing? The hypotenuse. How do we find the hypotenuse? Pythagorean theorem. So in order to find the hypotenuse, if you want, let's do it r squared, equals -5 squared plus -12 squared. Well, when you square a negative, it's still positive, so 25 plus 144 is 169. And if that's r squared and I square root that, we expect that you know your perfect squares. You get an answer of 13. So I can label my hypotenuse then as 13. Your hypotenuse is a distance from the origin to that point. That should always be a positive value. Okay, so they wanted us to find sine, cosine, and tangent. So the sine of an angle, of my angle, is the opposite over the hypotenuse, so -12 over 13. The ratio itself can be negative. The hypotenuse length can't be negative though, okay? The cosine of my angle is the adjacent side over the hypotenuse, so -5 over 13, sorry. And the last one, the tangent, is opposite over adjacent. -12 over -5, we want to write it as 12/5. Does So there's our three ratios. Again, we could ask you the reciprocal functions if we needed pretty easily in this situation. The number one thing though, you cannot have decimals in a fraction. That is the number one thing. So what does that mean? You shouldn't have decimals when you find the hypotenuse. You need to break down square roots. We'll shorthand this a second. That's the big thing. No decimals as we go through. Break down your square roots instead. That's an Algebra 2 concept, so we expect that we can just ask you to do that. We want to start talking about reference angles, and actually I'm going to move this down so I can see both at the same time. We did reference angles in Algebra 2, so I'm going to walk through this pretty quickly, but we call a reference angle theta prime. And theta prime is basically the acute angle. Did you see this word, acute? That means less than 90 degrees. It is on the terminal side of the angle and the horizontal axis. So we basically are saying, let's get to the x-axis as quick as we possibly can. Biggest thing though, reference angles are always positive. Okay, they are always positive, and that's the big thing. I'm going to show you three pictures because I want to look at each quadrant individually. And we did this in Algebra 2 the same way, so I'm going to keep you going that way. Let's look first at if an angle is in quadrant 2. The reason I don't start with quadrant 1 is because if it's in quadrant 1, then it is a reference angle because it's already acute. So that's why we start with quadrant 2. And I'm just going to stick my angle right here. Okay, so here's my angle theta. And the question is, where's my reference angle? Now, let me change colors a second. The reference angle means get to the x-axis as quickly as you can. Well, is it worth going backwards or is it closer to go forward? And I think you're going to say to me it's closer to go forward. This then is theta prime. And the question is, well, how do I find the measure then of that angle? Well, you have a couple of ways to do this. And I'm going to show you both in degrees and in radians. You could take in degrees 180 degrees minus your angle, theta. If I do it in radians, I would take pi minus my angle. And I'm going to write it both ways because, again, you're going to see it both ways. Okay. I'll just keep this color. Let me go into quadrant 3. And if I give you an angle in the third quadrant, let's say it's down here. So this is my angle theta. Let me change colors. And again, we're asking, is it quicker to go forward to the x-axis or backwards to the x-axis? And it is backwards. Now, even though I say backwards, my theta prime, my reference angle, has to be positive. So I've got to manipulate the way I actually write this. In order to find theta prime, I'm going to take my angle theta and I'm going to subtract 180. Because I want the overage, is basically what I'm asking. How far over did it go from 180? Or in terms of radians, I'm going to take my angle and subtract pi. Okay. Again, we're looking for the overage. Because the reference angle has to be positive, I've got to subtract them that way. The last one I want to look at is quadrant 4. So if I look at this, I'm going to pick this angle right here. Here's my angle theta. And is it quicker to go back to the x-axis, the negative x-axis, or forward to the positive x-axis? And again, it's quicker to go positive. So this is theta prime. How do you find theta prime? We're going to find theta prime by taking 360 minus my angle, or in terms of radians, 2 pi minus my angle. The reason, again, I show you both degrees and radians is because quite often, like the next example, we want it in terms of radians because we start you in terms of radians. Okay? Let me find a slightly different color on this one. So take a look in the next one. Find the reference angle for 11 pi over 4. Okay, now I got to be honest. I look at 11 pi over 4, and I don't necessarily know where that is. So I'm going to take the idea like we did in the last section, and I'm going to count my way around. Because it's over 4, I know it's a multiple of 45 degrees. So I'm going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This then, if I went a whole revolution around plus, this is 11 pi over 4. Okay? The only thing is I don't want to have to look at all of those revolutions. So what I'm going to do then is instead I'm going to say 11 pi over 4 is the same thing as 1, 2, 3 pi over 4. And I'm going to use this idea of 3 pi over 4. Now again, let me change my color and let's look at this. If here is my placement, is it quicker to go to the negative x-axis or back to the positive? And we know it's quicker to go to the negative x-axis. So I'm going to find this reference angle by taking, because it's in radians, I'm going to use 180, I'm going to use pi instead of 180, minus, and I'm not going to use 11 pi over 4, I'm going to use 3 pi over 4 because I know that they're just coterminal angles, and therefore I can use any version of that coterminal angle. Okay, now we need a common denominator, so I'm going to multiply this by 4 over 4. So 4 pi over 4 minus 3 pi over 4 is pi over 4. And this is my reference angle, theta prime. We also ask you for the cosecant of 11 pi over 4, which really we're asking you what's the cosecant at 3 pi over 4. Well, cosecant is the reciprocal of a sine. So the sine right here, it's an over 4, so it's negative square root of 2 over 2, positive square root of 2 over 2. And if I'm reciprocaling the sine, then I'm looking at 2 over the square root of 2, which I rationalize, and I get 2 square roots of 2 over 2, or just the square root of 2. Okay, it's a lot of stuff going on, but this is the idea. One, I'm coming back to this idea of coterminal angles, and then I'm using this reference angle to kind of help me then evaluate one of the trig functions. All right, taking a look at the next part, all students take Mr. Wilcox's stats classes, Wilcox's version. We said all students take calculus. And what we said is this meant all of the trig values were positive in the first quadrant, sine was positive in the second, tangent was positive in the third, cosine was positive in the fourth. The only thing I want to add to that quickly is the reciprocal functions. This truly means all 6 trig ratios are going to be positive in the first quadrant. Okay? In the second quadrant, sine is positive, but so is its reciprocal of cosecant. In the third quadrant, tangent is positive as well as its reciprocal cotangent, and cosine is positive as well as its reciprocal secant. That's positive in the fourth quadrant. And so all I wanted to do on this one is to actually make sure that we looked at it and said, yes, don't forget the reciprocal functions as well. Okay? Number 1, take a look. We're giving you not only the tangent value, but we're also trying to give you an idea of what location we're looking for. In this case, you take a look and notice that tangent is negative, and so is cosine. So we're wondering, where is both tangent and cosine going to be negative? Well, when I look at this, tangent is negative in 2 and 4, cosine is also negative in the second quadrant because cosine's positive in the fourth. So I have to be in quadrant number 2. Okay, so that's what this all students take calculus helps us with. So here's what I'm going to do. I'm going to make a picture in quadrant 2. Tangent is opposite over adjacent. So when I make my triangle in quadrant 2, I'm going to make a triangle. I know that the opposite is 5, the adjacent is 4. Now, you'll notice I didn't put the negative with the 5. Because look in quadrant 2, which value is negative, the 5 or the 4? Well, as I go, the 4 has to be the negative because I move left 4 and up 5 to get to that point. So please be careful as you're labeling these that you're actually labeling them correctly. Now, when I go through, I obviously need to find my hypotenuse or my value of r. So r squared is 5 squared plus negative 4 squared. 25 plus 16 is 41, and I can square root this. Now the question is, can you break down the square root of 41? And you can't because it's prime. So r is just the square root of 41. So now that I know that, let's find the sine of this angle. Well, sine is opposite over the hypotenuse. So 5 over the square root of 41. We're not okay with leaving a square root in the denominator. So when I rationalize, I get 5 square roots of 41 all over 41. Because 5 and 41 can't reduce, this is my answer. Please know your answer is positive because sine is positive in the second quadrant as above. So we need that to be a positive answer. Secant is the reciprocal of cosine. So if I look at this, 1 over the cosine, cosine is the adjacent over the hypotenuse. So the cosine would be negative 4 over the square root of 41. But I'm doing the reciprocal, so the square root of 41 over negative 4. Done. There's no need to do anything with it because the square root's in the numerator. So you're all set. The hardest thing about these extra questions is really where is your triangle supposed to be located? And the hardest part is figuring out which quadrant. That's why we tell you that all students take calculus. Okay? 2 more examples. In the second one, the sine is positive and in quadrant 2. That was really nice of us. So when I go to make my triangle, it's in quadrant 2. And the sine, which is opposite over hypotenuse, is 1/3. We're now looking for this distance here. One thing you should keep in mind, though, is that this cosine value needs to be negative. And so is the tangent. So whether we actually find it or not, you need to know that it's negative. Now I'm going to take the pre-calc way here a second because I'm going to start with cosine. I'm going to go this route. The sine squared plus the cosine squared should equal 1. And the reason I'm going this way is 1, I don't want you to forget about those identities. And 2, this actually is going to help me determine that it could be negative. Sine is 1/3. So when I square 1/3, I get 1/9 plus cosine squared equals 1. So I'm going to subtract 1/9. And I get that cosine squared then is 8/9. I'm going to square root, and when I square root, I get either a positive or a negative. In this case, what do I want? I want that negative. And I'm going to ask you to simplify this. So here we go. We have the square root of 8 over the square root of 9. The square root of 8 can be broken down into the square root of 4 times the square root of 2. So I have 2 square roots of 2 over 3, but I know I've got to keep the negative, so I have negative 2 square roots of 2 over 3. This is again why I chose to use the Pythagorean identity. You could get that with the regular Pythagorean identity or the Pythagorean theorem. It just isn't as much fun, in my opinion. But that's just me. Okay. The second one we do is tangent. And again, the tangent should be negative. Tangent is sine over cosine. So the sine is 1/3. The cosine is negative 2 square roots of 2 over 3. Okay? We know that if we multiply by a reciprocal, the 3's end up canceling. So I'm going to skip that work there a second. So we have 1 over negative 2 square roots of 2. To simplify this, I'm going to only multiply by the square root of 2. So I get negative 2 square roots of 2, and I just moved this negative up top. This is 2, so 2 times 2 is 4. There's your final answer. Okay? And again, we're dealing with square roots. Please, again, there are no decimals in fractions, so as you go through, everything needs to be left in square roots. The last one starts us getting into stuff that's coming up. And we give you that the cosine of an angle is negative square root of 2 over 2. And the question is, what could that angle be? Okay, I'm going to draw a picture. Because it's the square root of 2 over 2, I know it has to be 45 degrees. Is it in quadrant 1? No, because the cosine would be positive. Is it in quadrant 2? Well, yes, because I know that it'd be a negative cosine and a positive sine. So I want this angle, I also want this angle, and I know I don't want the fourth quadrant because cosine's positive there too. So the question is, if I look at these 45-degree angles, what are they in terms of radians? Now in terms of degrees, this is 135, and this is 225. But again, I don't want degrees, I want radians. So 135 degrees is 3 pi over 4, and 225 degrees is 5 pi over 4. And actually, I expect that you know those without having to convert them. And so take a look. These are the two values in terms of radians that give me a cosine of negative square root of 2 over 2. And right now we're going to take everything off the unit circle. So if you had to look at your unit circle in order to be able to find that, I'm perfectly fine with that today. In the next couple of days, though, we're going to have to figure out how to do that without our unit circle, or at least maybe quicker than having to think about, oh, what quadrant, how does it work, things like that. So that's section 4.4. Appreciate you watching. Again, we'll be, tomorrow we're going to be graphing all these trig functions, so keep that in mind.